So now, more interestingly, I might be able to actually show you something a little bit more interesting in terms of testing circuits. So there's a different test circuit, and that test circuit, its debouncing effect will be a little bit more obvious to us. And what the debounce circuit does is the following. What you're going to see is we're going to take that debouncer, the one that we designed, it's exactly the same, switch as an input, debounce as an output. And then we're going to take these edge detectors that we have developed previously. Okay, so we're gonna connect, well, we're gonna connect a button. One will pass through the debouncer, the other one will go directly in here. Our ultimate goal is to count how many press of the buttons, of that push buttons we did. So one will go through the debouncer, one will want. So this one here, it just basically gives me a tick every single time a positive edge happens. Basically, I'm counting the positive edge, and in turn, I'm actually counting how many times I press the button. These two here are basically the same. We just instantiate a couple. Some we can connect directly to the switch, some we connect to the debounce output, and then we connect it to a binary counter. It's pretty much the same exact counter we have developed before. The only difference is I have to modify the code a little bit and add an enable, because I will not make the counter count using the tick as its clock. This is actually not a good habit. So everything here operates in the same clock, which is 100 megahertz. Okay, and again, and this tick here might not be a good clock, and the other reason why is because I will be using the melee output, and the melee output is not very stabilized, so that is not good as a clock. So what we're going to be doing is I added a little bit of an enable here, so I'll only increase the counter if its enable is asserted. It's the same exact counter. We're going to instantiate a couple of here, and the output, what we're going to be doing is a displayed multiplexer hex. Basically, it's some sort of a block that has a bunch of other things inside it that takes hexadecimal numbers in and will output some sort of a 7-segment display. It's something you have probably seen before. Okay, so we're going to take those counter, we're going to consider them to be 8-bit counter. We're going to connect the lowest significant bits here and the more significant bits in here, and so forth. Well, the display multiplexer you're going to see that I designed is actually not for 0 to 3. It will go from 0 to 7 because I do have the nexus here, and I have 8 digits available to me. So what I will be doing is I'll be displaying some on the lower, and the other ones are on the lower of the second part. If you know, it's like the nexus has 2 parts. So let's do that. Okay, so let's go to Vivado and see the implementation for this particular circuit. So we're going to go in here. Okay, so what you see in Vivado is I have a lot of files in here, including the top file, and that top file is actually what I'm connected, or what I pretty much interface with the FPGA. But what I really want you to see is the following. Like if I click on the schematic, I ran all of this, so it took some time. You're going to see that it's basically a direct implementation of what happened. I basically took the rising edge detect, the melee version. It's the same exact code. I basically instantiated a couple of copies. Of course, one will be connected directly to the switch. So you can take a look at the switch. You can see that one of them is connected directly to it. I called it a switch. And the other part of the other input of the switch is connected to the debouncer circuit. So the debouncer goes in here and actually goes to the debounce one. And then from there, it's basically the same counter. It's a binary counter that we have. Again, I just added an enable in here and an enable in here. And then we take it to the 7-segment display thingy. And of course, if I actually expand that 7-segment display or anything else, I can actually see its components. For example, if I do that in here, you get to see that probably have a multiplexer and another counter. Well, it's the same binary counter that we used. This I'm using as a timer, and in that particular case I do care about its value because I'm controlling the multiplexer, I'm controlling the decoder. This is something you've seen, and this is a hex to the 7-segment. What I really care about more is actually what am I doing in here? Okay, how am I displaying it? So let me just show you. Here. Okay, so here's the FPGA. Again, it's the same thing. So the middle point will actually reset, and the bottom is actually basically the switch. What you see in here is this one in here is the unbounced, or like basically the bouncy one. If it bounced, you're going to see a count in here, and this one here is the debounced one. So let me just press 1, and you can see both of them counted 1 and 1. No bounce happened. And I'm gonna do again. I'm gonna do it again. Sometimes it happens, like I do something like sometimes I move my finger and it does. Okay, so let me just do this here, and you're gonna see a discrepancy at some point. I'm gonna reset. I'm gonna do this. There you go. Here we go. Basically a bounce happened. The counter counted a couple, or like one extra than necessary. So it counted here as a 3, and now here what I have is a 2 because it got debounced. It didn't figure it out. Okay, so this is actually neat, and I want you to go through the code on your own and see it. It's really not that difficult to see. It's basically connecting all these boxes together. Again, the only thing I changed from the binary counter perspective is the following. Let me just show you here. So basically that's the binary counter. I just added an enable, and what I really did is I went in here with enable and I said, okay, usually it used to be register, or the next state is just basically register current state plus one. I just added like this little logic that asks, is the enable asserted? If it is, add. If not, just do not add. And the rest of it is pretty simple. Constraint file as well. You need to make sure that the 7 segments and whatnot, the clock is here connected. The other thing is basically the 7 segments and the anodes basically for the transistors that connect which one of these or control which one of these 7 segments is active, the reset and the switch, and you get the idea. And of course I'm not exposing to the PMOD header the JA anymore, so I basically will comment them here. And of course there are, not only can you actually debounce it using an early debouncer or like a late debouncer, a delayed debouncer like we saw. Maybe it is really important for you and you can't wait for this 20 to 30 millisecond. Another version of it is actually an early debouncer, and you will be implementing this on your own. What the early debouncing does is the minute it catches the first 0 to 1, it just basically stabilizes it for 20 milliseconds, and if it stays at 1, it continues to 1. If it goes back to 0, it just makes it back to 0. Well, it'll count it again for another 20 milliseconds or whatnot. It's just basically the interface you're going to see, it's a lot earlier. So you get to see in here, like it's bouncing, but it captured it here.